Lewis structure, also known as a Lewis dot structure, applies to atoms, ionic compounds, and molecular compounds. In this particular video, we're going to cover molecular compounds. Let's begin. Molecular compounds, remember, are compounds made up of nonmetals and nonmetals. And not only are they made up of those two particular elements, but they are joined together by covalent bond. Covalent bond is nothing like an ionic bond. Ionic bonds are connected together via the electrostatic force, the opposite charge, negative and positive. As whereas a molecular compound forming a covalent bond, they're able to connect together via the sharing of electrons. Now, the sharing of electrons can be visualized in the Lewis dot structures. For example, like this. The lines here represent the sharing of electron between the carbon and the hydrogen. How many? There are two shared electrons between one line. One is coming from the carbon and the other one is coming from the hydrogen. Now you see all these little dots here, and those dots are called lone pairs. Now again, bonds are written as a single line and represents two shared electrons. The lone pairs that are on here, there are in sets of two free electrons. They are not within the bond. They do not bond, but they are still part of the valence electron within phosphorus, bromine in this case. Now, why are they arranged in such way? If you see, here's carbon. There are these four lines around them. This chlorine has these 6 dots around them, and you see hydrogen, there's no dots around them. Now, what are they trying to do? Well, these molecules are trying to fulfill what is the octet rule. This carbon is trying to fulfill 8 electrons around themselves, and it is. Look, this is 2, 4, 6, 8. Since each line represents 2 electrons, there's 8 around that carbon. So they have fulfilled what is called the octet rule. For this chlorine, it also fulfilled the 8, the lone pairs, 2, 4, 6, and then that line is 2 electrons, so 8 total. What about for hydrogen? So hydrogen is one of the exceptions. They will fulfill what is called the duet rule. So hydrogen will only need to fulfill the duet rule. And so they could go maximum only up to 2, and that's what they'll try to do. Look for here, the H2O. Hydrogen is only connected to 1. That line represents already 2 electrons, so it doesn't need any more lone pairs in order to fulfill the duet rule. They're arranged in such a way so that, again, to fulfill the octet rule and for duet rule for hydrogen. So how do we even write this? How do we know this nitrogen has to have 2 lone pairs and 3 hydrogens? How do we draw this? To draw the Lewis dot structure, we need to follow some rules. Now, these are the rules, and I will go over each rules with you as I draw PCl3. Let's begin with the very first rule. It says place a singular element in the center and then surrounded by the remaining elements. So if you look at PCl3, the singular element is phosphorus, P. So I'm going to put that in the middle and then chlorines around it. So this is sort of like my skeletal structure. Number 2, then it says count total number of valence electrons. So I'm going to count the total number of valence electrons for phosphorus and chlorines. There's 1 phosphorus and 3 chlorines, and phosphorus has a valence electron of 5, chlorine of 7. And that we can tell by the periodic table. You just go across the column. If I add all of this up, you will get 26 valence electrons. Now, with this valence electron, you're able to draw in those lines and the dots. There's 26 available. Our goal is to utilize all of them and fulfill the octet. Now, you can see on number 2, there is additional rules. if dealing with a charged compound. At the moment, we are not dealing with charged compounds, so I'm going to skip on over. Yes, there will be more regarding charged compound later in the video or in the next part. Attach all surrounding to the center with the single bond, says rule number 3. So I'm going to go ahead and place single bonds from outside to the middle. Remember that the single bond represents how many electrons? 2 electrons. So therefore, I'm going to subtract 2, 4, 6 from the valence electrons. So minus 6. Now I have 20 left over. So the 6 electrons I have used is the single bond here. Number 4, complete an octet for the surrounding atom first. The surrounding atoms are the chlorines. Currently, the chlorine only has 2 electrons around them. 2 here, 2 here, 2 here, because of that line. So I need 6 more in order to fulfill the octet. And that 6 more is going to be the lone pairs. So I'm going to place 2 on top, 2 on the left, and 2 on the bottom. That's minus 6. I have utilized 6, so I'm left with 14. Let's go ahead and place the rest. Minus 6 again. Minus 6, and I'm left with 2. So number 4 says, complete the octet for the surrounding atom first. If there are extra electrons, and we have 2 left, add remaining to the central element. So here's my center, and the center will need 2 electrons added to it. So minus 2. So I'm left with 0. The phosphorus now has fulfilled the octet as well. 2, 4, 6, 8. Now remember that you need to fulfill the octet for the outside atom first. Work on those first before you come into the phosphorus. Number 5 says, if the central atom has fewer than 8 electrons, well, that's not the case, then you need to form double and triple bonds. More on that on a later. So for now, this is the Lewis dot structure for phosphorus trichloride. You're going to follow the very same rule for carbon tetrafluoride. Try this and come back and check the key. And here is the key. Now we're going to be dealing with a compound that has a charge. Let's start with number 1. I want you to try number 1 by placing the singular element in the center and then surround it by the remaining elements, and come back and let's move on together from there. So here we have nitrogen and 4 hydrogens around them. Nitrogen has a valence electron of 5, right? Yeah, 5. And the hydrogen has 1 each. Okay, that's total of 9 valence electron. On number 2, it says to count the total valence electron, which we did. Now, it has an additional rule, which says if dealing with the charged compound, and it's plus charge, add 1 for each negative charge and subtract 1 for each positive charge. And at this point, at this charge, it's positive 1. So we're going to take out 1. So we are dealing with total of 8 valence electron. Then it says attach all surrounding to the center with the single bonds. Then I'm going to go ahead with single bonds here. Okay, that's minus 8 total, and I'm left with 0. So there's no more. Now there is something that I skipped. I apologize. This is use brackets to show charge, and that is true. You're going to use a large bracket like this and put a plus sign to show that this is positively charged compound. Now, did this fulfill the octet? Sure. For nitrogen, it definitely did, 2, 4, 6, 8. For hydrogen, it fulfills the duet. So they're pretty happy as well. So this actually is the complete Lewis dot structure for ammonium. Now we're going to get into carbon dioxide, CO2. Let's start from, I want you to actually try this. Go ahead all the way up to number 4, complete an octet for the surrounding atom first, up to right there. And then I'll meet you right there, and then we'll go on from that point together. So you're probably right here, where you have completed the octet for the surrounding atoms first. We're left with 0. We're quite not done yet. And this is because if the central, right, this is rule number 5, if the central atom has fewer than 8 electrons, and in this case right now we only have 4 electrons. It says form double or triple bonds by moving electrons until all atoms have an octet. So what does that mean? Where am I getting the electron from? You're going to get it from the surrounding atoms. So surrounding atoms are these oxygen. So I'm going to borrow one of these pairs in order to form another bond between the carbon and the oxygen. So for example, I'm going to take this one. I'm going to take this one right here and then form a double bond. So if I were to rewrite this, it would be C, the one that came from those lone pairs, oxygen, and I'm going to put the rest of the dots. If you see this image, you can see that this oxygen that's on the right actually has fulfilled the octet still. 2, 4, 6, 8. This oxygen still has 8. This carbon has 2, 4, 6. So it still lacks octet. So I need another bond. I'm going to borrow from the other side of the oxygen here. Utilize those 2 electrons to form a bond. Why 2? Because each bond represents 2 electrons. So here's my oxygen. I'm going to redraw this, double bond it from here, and we still have the double bond here. Now, did it fulfill the octet for carbon? Let's see, 2, 4, 6, and 8. Yeah, so that particular carbon fulfilled the 8 electrons, and so did the oxygen, 2, 4, 6, 8. So this is your complete this is the complete structure for carbon dioxide, the Lewis dot structure for carbon dioxide. Now go ahead and try this learning check for SO2. And here is the key. The dots on the corner